Hi everyone. In this video, we are going to study basic concepts of probability. Let us define probability. Probability is a measure that is associated with how certain we are of outcomes of a particular experiment or activity. An experiment is a planned operation carried out under controlled conditions. Random experiment is an act whose outcome cannot be predicted with certainty. For example, tossing of a coin is a random experiment. Though we know that the outcome of the experiment will result either head up or tail up, we cannot certain what it will be. Other examples of random experiments are rolling a dice and football game. A result of an experiment is called an outcome. An event is any combination of outcomes. Uppercase letters like A and B represent events. For example, if the experiment is to flip one fair coin, event A might be getting at most one head. The probability of an event A is written P of A. Another example, in the random experiment of rolling a die, coming of one is an event. Coming of two is the other event. And coming of even number is another event. The first two events are called simple events because they correspond to only single outcome. Coming of an even number is called a compound event because it corresponds to more than one outcome of the experiment, namely 2, 4, and 6. The sample space of an experiment is the set of all possible outcomes and is denoted by S. Examples: number 1. In tossing a fair coin, the sample space is S equals H and T, where H equals head and T equals tail are the outcomes. Example 2. In tossing two fair coins, the sample space is S equals HH, HT, TH, and TT. Example 3. In rolling a die, the sample space is S equals 1, 2, 3, 4, 5, and 6. In throwing two dice, the sample space is given here. The sample space starts with 1, 1 and ends up into 6, 6. Example 5. In a pack of cards, there are 4 suits, which are hearts, clubs, diamonds, and spades, and 13 cards for each suit, that is from ace through king. There are 52 outcomes in the sample space. Each element of sample space is called sample point. Example, in rolling a die, sample space S equals 1, 2, 3, 4, 5, and 6. Number 4, that is the number 4, is a sample point. Today we're going to study classical definition of probability. The probability of happening of an event E is defined as the ratio of the number of outcomes favorable to the event E to the total number of outcomes. In symbol, this is P of E equals the fraction whose numerator is number of favorable outcomes over the denominator total number of outcomes, or we say sample space. In symbol, this is equal to the number of outcomes for E over the number of the sample space. For a sample space S and an outcome A of S, the following two properties are satisfied. Number 1, the probability of A, denoted by P of A, is between 0 and 1 inclusive. In symbol, we write P of A is between 0 and 1 inclusive. Second, the sum of the probabilities of all the outcomes in S equals 1. In symbol, we write the probability of I equals 0 up to n of P of A sub I. This is equal to 1. Let us have example 1. A die is rolled once. Write the sample space and find the probability of letter A. Number 3 is shown up. Letter B, getting an odd number. Letter C, getting a number greater than 4. Letter D, getting prime number. We have a picture of a die on top of our screen. In rolling a die, the sample space is S equals, the elements are 1, 2, 3, 4, 5, and 6. And then, let us write our formula. The probability of event E equals the number of favorable outcomes all over the total number of outcomes. Let's begin with problem A, that the number 3 is shown up, and we write P of 3. In our sample space, we can see that there is only one element of 3. So we write here 1 all over the total number of outcomes is 6. So the answer here is 1 over 6. And this answer we will write opposite problem A. Let us go now to problem B. The probability of getting an odd number. So we write P of odd. In our sample space, we can see that there are three odd numbers, namely 1, 3, and 5. So we write here 3 in the numerator over 6 as the total number of outcomes. And this 3 over 6 can be simplified into 1/2. So our answer for the probability of getting an odd number is 1/2. Let us copy this answer opposite letter B. Then let us proceed to letter C. The probability of getting a number greater than 4. So we write here P of greater than 4. In our sample space, there are two numbers that are greater than 4, namely 5 and 6. So we write here 2 over 6. And then to simplify, this is equal now to 1 over 3. And this answer we will write opposite letter C. There we go. Then let us proceed with problem D. The probability of getting prime number. So we write P of prime. In our sample space, there are three prime numbers, namely 2, 3, and 5. Remember, prime numbers are numbers greater than 1 whose factors are 1 and itself. In our solution, we write 3 in the numerator over 6. And when we simplify, this is equal to 1 over 2. Let us copy this answer opposite letter D. There we go. So we are done with our example 1. Let us go to example 2. A jar contains 3 red marbles, 7 green marbles, and 10 white marbles. If a marble is drawn from the jar at random, what is the probability that this marble is letter A, white, letter B, red, letter C, blue? Step 1, let us compute for the sample space. So we add 3 for the red marbles plus 7 for the green marbles plus 10 for the white marbles. And this is equal to 20. And then let us write our formula, and it is now written here. Let us begin with our first problem to get the probability of white. And this is equal to, in the numerator, we write 10 because there are 10 white marbles over the total number of outcomes, which is 20. So this is 10 over 20. And the simplest form is 1 over 2. This is our answer. Let us copy this opposite problem A. Let us proceed with problem B to get the probability of getting a red marble. So we write P of red. This is equal to 3 because there are 3 red marbles all over the total number of outcomes, which is 20. And this 3 over 20 is already in simplest form. So we will just copy this opposite letter B. Let us proceed now with problem C. What is the probability of getting a blue marble? Getting a blue, this is P of blue, equals 0 because there is no blue marble in the jar as given in the problem. So this is 0 over 20 and simplified into 0. It means it is impossible to get the blue marble inside the jar. So we are done with our example 2, and this is our final answer. Let's proceed with example 3. In a deck of cards, find the probability of getting a letter A, queen, letter B, diamond card, letter C, black card. In our sample space, there are 52 cards in a deck of cards. Our formula is given, and let us proceed now with our problem A. To get the probability of getting a queen. In a deck of cards, there are 4 queens. So we write here 4 over the total number of outcomes, which is 52. So this is 4 over 52. Then to simplify, this is equal now to 1 over 13. This answer we will write opposite letter A. Then let us proceed with problem B. Finding the probability of getting a diamond card. So we write P of diamond card, and this is equal to, in the numerator we write 13, because there are 13 diamond cards in the deck of cards. So this is 13 over 52. And when we simplify, this is equal now to 1 over 4. This answer we will write opposite letter B. And then let us now proceed with letter C. Finding the probability of getting a black card. So we write P of black card. This is equal to 26. When we say black card, it means the group of clubs and the group of spades combined. So that is 13 plus 13. So in the numerator we write 26 all over the total number of outcomes, which is 52. And then let us simplify this, reduce to lowest term, and this is equal to 1 over 2. And this answer we will copy opposite letter C. We are done with our example 3, and this is our final answer. Today we're going to study properties of probability. Let us consider some properties of probability, and this is the first one. The union of two events, E and F, denoted by E union F. Take note that the union is symbolized by U, is the set of outcomes that are in E, or in F, or in both. The second property, the intersection of two events, E and F, denoted by E intersect F. Take note that the symbol for intersection is an inverted U, is the set of outcomes that are in both E and F. Property number 3, two events E and F are said to be mutually exclusive or disjoint if they cannot occur at the same time. That is, E intersect F equals 0. In relation to the union and intersection of events, we have this addition rule. It says the probability of the union E and F equals probability of E plus probability of F minus the probability of E intersect F. Property number 4, the complement of an event E, denoted by E with exponent C, is the set of outcomes in the sample space that are not in E. We have this formula: the probability of E complement equals 1 minus probability of E. Let us have some examples. Here is example 1. A card is drawn from a standard deck. Determine whether the pair of events given below are mutually exclusive. Event E, the card drawn is an ace. Event F, the card drawn is a heart. First, let us see all the cards in a deck of cards. Next, the ace of hearts belongs to both sets. This is the ace of hearts, means the E intersect F, that is the ace of hearts, is not equal to 0. Therefore, the events E and F are not mutually exclusive. This is our final answer. Let us have example 2. A family has 3 children. Determine whether the following pair of events are mutually exclusive. Event M, the family has at least 1 boy. Event N, the family has all girls. For the solution, we will write first the sample space that consists of 8 possibilities. This is our sample space. Next, we will list both the sets. For the set M, we have BBB, BBG, BGB, BGG, GBB, GBG, and GGB. For event N, only one element, and that is GGG. Clearly, we can see that M intersect N equals 0, or we say there is no common between M and N. Therefore, the events M and N are mutually exclusive. This is our final answer. Example 3. If a die is rolled, first question, what is the probability of obtaining an even number or a number greater than 4? Question 2. What is the probability of obtaining an even number and a number greater than 4. For our solution, first, let us assign E, this is the event, for an even number. And let F be the event for number greater than 4. Let us write the sample space, and that is numbers from 1 to 6. Then let us write event E, whose sample points are 2, 4, and 6. For event F, elements are 5 and 6. For the first question, we will solve even number or greater than 4. We will write here E union F. Take note, the word or here denotes union of event. So we have the elements 2, 4, 5, and 6. Now, for the probability of E union F, this is equal to the fraction 4 over 6. We write here 4 because there are 4 elements in our E union F. We write here 6 because there are 6 elements in the sample space. And then we will simply reduce this to lowest term. So we have 2 over 3. Let us answer the second problem, and that is even number and greater than 4. So we write E intersect F. Take note that this word "and" here denotes intersection of events. So this is equal to the set with element 6. Therefore, the probability of E intersect F equals 1 over 6. We write 1 here because there is only one element of E intersect F. Again, we write number 6 here because there are 6 elements in the sample space. Let us have example 4. If a card is drawn from a deck, use the addition rule to find the probability of obtaining an ace or a heart. First, let us assign A to be the event that the card is an ace. Then, we let H to be the event that the card is a heart. Since there are 4 aces and 13 hearts in the deck, and we know that the sample space equals 52, so we write here the probability of A equals 4 over 52, and the probability of H equals 13 over 52. Furthermore, since the intersection of two events is an ace of hearts, so we write P of A intersect H equals 1 over 52. Then, for the addition rule, we write here P of A union H. Take note, we see here the word "or" that denotes union. And this is equal to the addition rule. That is equal to P of A plus P of H minus P of intersection of A and H. So we do the substitution. P of A is now 4 over 52 plus the P of H is 13 over 52 and minus the P of A intersect H, that is the 1 over 52. And when we do the operation, we have 16 over 52. We reduce this to lowest term, and that will be equal to 4 over 13. This is now our final answer. Example 5. 2 dice are rolled, and the events F and T are as follows. Event F, the sum of the dice is 4. And event T, at least one die shows a 3. Find the probability of F union T. First, let us remember we have a table that shows rolling of 2 dice. Then we list the event F and event T and the event F intersect T. Let's begin with F, and we have here 1, 3, 2, 2, and 3, 1. Next is the event T. So we have here many elements, starting with 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 1, 3, 2, 3, 4, 3, 5, 3, and 6, 3. Now, for the F intersect T, we have 1, 3 and 3, 1. Then, let us write the addition rule. So, this P of F union T equals the P of F plus the P of T minus the P of F intersect T. So let us do the substitution. P of F will be 3 over 36. We write here 3 because there are 3 pairs in the event F. Over 36, there are 36 possibilities of pairings. Then plus the P of T, so we have 11 over 36. We write here 11 because there are 11 pairs in our event T. Over 36, again there are 36 possibilities in the rolling of 2 dice. Then minus the intersection. So we write 2 over 36. We write here 2 because there are 2 pairs in our F intersect T. And then let us operate the 3 fractions, and the answer is 12 over 36. Let us reduce this to lowest term, so we have now 1 over 3. This is now our final answer. Let's have example 6. The probability that a student in the college owns a car is 1/3. What is the probability that a student does not own a car? First, let us acknowledge that the P, or the probability for student owns a car, is 1/3. The problem is asking about the probability that the student does not own a car. Take note that these two events are complement of each other. We have a formula for the complements. So we have here P of complement of an event equals 1 minus P of the event. With regard to our problem here, we may write the P that student not own a car equals 1 minus P, or probability that a student owns a car. Let us simply substitute the value in our P, student owns a car, and that is 1/3. So we have 1 minus 1/3, and the answer is 2/3. This is the probability that a student does not own a car. This is our final answer. Today we're going to study conditional probability. What is conditional probability? Whenever we are finding the probability of an event E under the condition that another event F has happened, we are finding conditional probability. This is the symbol that is used for conditional probability, and this is read as the probability of E given F. It denotes the problem of finding the probability of E given that F has occurred. This is the formula to be used. The probability of E given F equals this fraction, where the numerator is the probability of E intersect F, over the denominator, and this is the probability of F. Let us see some examples. This is example 1. A single die is rolled. Find the conditional probability of obtaining an even number given that a number greater than 3 has shown. First, let us assign E to be the event that even number shows. Let F be the event that number greater than 3 shows. So we are looking for the conditional probability of E given F. Let us list event E, and these are 2, 4, and 6. And the elements of event F equals 4, 5, and 6. We know that the sample space has 6 elements. Now, for the E intersect F, there are 2 elements, and these are 4 and 6. Therefore, the probability of F equals 3/6. We write here 3 because there are 3 elements for F. And we write here 6 because there are 6 elements in our sample space of rolling a die. Next, the probability of E intersect F, and this is equal to 2/6. We write here 2 because there are 2 elements in the E intersect F. Again, we write 6 in the denominator because there are 6 elements in the sample space. Now we write our formula and we will do the substitution. In our numerator, the P of E intersect F is 2 over 6, and in the denominator, the P of F is 3 over 6. Then let us write this complex fraction into 2 over 6 times 6 over 3. And then we can cancel the 6 and the 6, and our final answer will be 2 over 3. This is now the conditional probability required by the problem. Let us have example 2. Given P of E equals 0.5, P of F equals 0.7, and P of E intersect F equals 0.3. Find the following. Letter A, P of E given F, and letter B, P of F given E. Let's begin with our A. Our formula will be like this, and we will do the substitution coming from the given. So we have now 0.3, that is the P of E intersect F, over P of F is 0.7. We will simplify this fraction, and this is equal to 3 over 7. Now for letter B, we have P of F given E, and this is equal to P of F intersect E over P of E. Let us do the substitution now. This P of F intersect E is just the same with our P of E intersect F. So we will use this value 0.3 here over the P of E, that is the 0.5. Let us simplify this. This is the same with 3 over 5. These are our final answers. Let's have example 3. Given two mutually exclusive events, E and F, such that P of E equals 0.4, P of F equals 0.9, find P of E given F. For our solution, since E and F are mutually exclusive, it means the P of E intersect F equals 0. Now, using our formula to find the conditional probability P of E given F, we will substitute the values 0 in the numerator over the P of F is the 0.9, and the answer is 0. This is our final answer. Example 4. Given P of F given E equals 0.5 and P of E intersect F equals 0.3, find P of E. For our solution, let us first write the formula that P of F given E equals P of F intersect E in our numerator over the denominator P of E. And then let us substitute the corresponding values. So we have now 0.5 equals 0.3 over P of E. In this equation, we can now solve for P of E. Let us simply interchange the position of this 0.5 and the denominator P of E. So we have now P of E equals 0.3 over 0.5. Then we can now solve for the P of E. This is equal to 3 over 5. This is our final answer. Let us have example 5. In a family of 3 children, find the conditional probability of having 2 boys and a girl, given that the family has at least 2 boys. For our solution, first let us assign E equals the family has 2 boys and a girl, and F equals the family has at least 2 boys. Then we take note that we want to get the P of E given F. We list now the sample space along with the events E and F. For our sample space, we have here 1, 2, 3, 4, 5, 6, 7, 8 sample points. Then for our E, we have 3 elements, and these are BBG, BGB, and GBB. For event F, we have 4 sample points, and these are BBB, BBG, BGB, and GBB. We can see that the E intersect F has 3 elements, and these are BBG, BGB, and GBB. Now, we can notice that P of F equals 4 over 8. We write here 4 because there are 4 elements in our event F. And in our denominator is 8 because there are 8 elements in the sample space. And the P of E intersect F equals 3 over 8. We write here 3 because there are 3 elements in our E intersect F. Over 8 because again there are 8 elements in the sample space. Writing our formula now, and let us do the substitution. So we have now this P of E intersect F is 3 over 8 over the P of F is 4 over 8. For this complex fraction, we may write 3 over 8 times 8 over 4. Then we can cancel the 8 and the 8, and the final answer will be 3 over 4. This is our final answer. Today we're going to study independent events. What are independent events? Whenever the probability of an event E is not affected by the occurrence of another event F and vice versa, we say that the two events E and F are independent. If the events are not independent, then they are dependent. This is the formal definition of independent events. Two events E and F are independent if and only if at least one of the following two conditions is true. Number one, the conditional probability of E given F equals the probability of E. Or number two, the conditional probability of F given E equals the probability of F. Take note, two events E and F are independent if and only if the probability of E intersect F equals the probability of E times the probability of F. Let us see some examples. Example 1. Given the conditional probability of B given A equals 0.4. If A and B are independent, find the probability of B. For our solution, if A and B are independent, then by definition, the conditional probability of B given A equals the probability of B. Therefore, the probability of B equals that same value, 0.4. This is our final answer. Example 2. A coin is tossed 3 times and the events E, F, and G are defined as follows. For event E, the coin shows a head on the first toss. Event F, at least 2 heads appear. Event G, heads appear in 2 successive tosses. Determine whether the following events are independent. Letter A, events E and F. Letter B, events F and G. Letter C, events E and G. For our solution, first we're going to list the sample space, the events, their intersections, and the corresponding probabilities. Starting with the sample space. There are 8 possibilities in the sample space, and these are first HHH and HHT, then HTH, followed by HTT, and then THH. Next is THT, then TTH, and the last is TTT, followed by the event E, and the elements are HHH, HHT, HTH, and the last HTT. The probability of E equals 4 over 8. We write here 4 because there are 4 possibilities in the event E. And the denominator is 8 because there are 8 possibilities in the sample space. We can reduce this to lowest term, so 4 over 8 equals 1/2. Next is event F, and the possibilities are HHH, then HHT, followed by HTH, and the last is THH. For the probability of F, this is equal to 4 over 8. In the numerator, we have 4 because there are 4 elements in our event F. Again, our denominator is the number of sample points in our sample space. So 4 over 8 is also equal to 1/2. Then the event G, and the elements are HHT and THH. For the probability of G, we have 2 over 8. We write here 2 because there are 2 elements in our event G. Number 8 is here because there are 8 elements in our sample space. The 2 over 8 is equal to 1/4. Then we will continue with our E intersect F, and we have 3 elements for that. For the probability of this E intersect F, this is equal to 3 over 8. There are 3 elements in our E intersect F, so we write here 3. And number 8 is again coming from the number of elements in the sample space. Next is the intersection F intersect G. We have 2 elements here. So the probability of F intersect G equals 2 over 8. And 2 over 8 is simplified into 1 over 4. And then the E intersect G, there is only one element, and that is the HHT. And the probability of E intersect G equals 1 over 8. Now, let us solve for letter A. So we write here, for these events E and F to be independent, we must satisfy this equation, that P of E intersect F is equal to the P of E times the P of F. Let us get the corresponding values from this side. So we will have 3 over 8 for this P of E intersect F. And we can see that this is not equal to the product of P of E times the P of F, because 1/2 times 1/2 will give us 1/4, and it is not equal to 3 over 8. Therefore, E and F are not independent. So let us write the remarks opposite letter A. Let us solve for letter B. F and G will be independent if it satisfies this equation. P of the F intersect G equals P of F times the P of G. Again, let us get the corresponding probabilities from these values. So we have the P of F intersect G is 1/4, and this is not equal to the P of F, and that is 1/2, times the P of G is 1/4. So when we get this product, it will have the 1/8, which is not equal to 1/4. So we may say now that these F and G again are not independent. Let us write our remarks opposite letter B. Let us now solve for letter C. We now look at this equation to prove whether E and G are independent. Let us substitute the values, so the P of E intersect G will be 1/8, and this will be equal to the P of E, which is 1/2, times the P of G, and that is 1/4, and the product of 1/2 and 1/4 is 1/8, which is equal to our left side. So we say that the events E and G are independent. So let us write our remarks opposite problem C. So this is now our final answer. Example 3. Carlos plays college soccer. He makes a goal 65% of the time he shoots. Carlos is going to attempt 2 goals in a row in the next game. Let A is the event Carlos is successful on his first attempt. So that is P of A equals 0.65. Let B is the event Carlos is successful on his second attempt. Again, the P of V equals 0.65. Carlos tends to shoot in streaks. The probability that he makes the second goal, given that he made the first goal, is 0.90. We have here 4 questions. Let's begin with the first one, letter A. What is the probability that he makes both goals? First, let us write the given. The P of A, 0.65. P of B is 0.65. This is the conditional probability. P of B given A, that is 0.90. To solve letter A, we need to use conditional probability. Our formula is P of B given A equals P of A and B all over P of A. We can rewrite this formula as P of A and B equals conditional probability of B given A times P of A. Then we substitute the values. This P of B given A is 0.90 multiplied by P of A, that is 0.65. And the product is 0.585. This is our P of A and B. Let's copy this answer below A. Then we go to problem B. What is the probability that Carlos makes either the first goal or the second goal? For this problem, we will use addition rule. The formula is P of A or B equals P of A plus P of B minus P of A and B. We substitute the values for P of A, P of B, and for this P of A and B, the value is what we found in this problem A. So the values will be 0.65 plus 0.65 minus 0.585. Finally, the answer is 0.715. This is the answer for problem B. Then we go to problem C. Are A and B independent? As a rule, A and B are independent if the conditional probability B given A equals P of B. In the given, the P of B given A is 0.90, that is not equal to P of B, that is 0.65. Therefore, A and B are not independent. So for letter C, we write not independent. And problem D, are A and B mutually exclusive? Two events are mutually exclusive if they cannot occur at the same time. However, Carlos can make both the first and second goals, as calculated in part A, or in this problem A. In fact, the value is 0.585. So we conclude, therefore, events A and B are not mutually exclusive. For problem D, we write here, not mutually exclusive.